So in this example, we're told we have a steady flow of air passing through this elbow nozzle assembly. So we have a flange here, goes through an elbow, and then there's this converging diverging nozzle, and then the air discharges out into the atmosphere. We're told the diameter of the pipe here at inlet 1, as well as the pressure and temperature and velocity there. And then we're told that the air goes through this converging diverging nozzle and discharges to the atmosphere. We're also told at this exit plane here what the diameter is and the temperature and velocity of the air as it comes out here. So question A is, first of all, is the flow through this elbow nozzle assembly adiabatic? And question B is, determine the components of force in the attachment flange. So what are the forces here required to hold the elbow nozzle assembly in place, and we can neglect gravity. So let's start with the first part, part A. Is the flow adiabatic? So if you recall, for a compressible flow, if the flow is adiabatic, then the stagnation temperature will remain constant. So if adiabatic, then the stagnation temperature will be a constant. That you'd have to go back through the notes to see how we arrived at that. It basically comes from the first law of thermodynamics. But anyway, we need to find that we need to check to see if the stagnation temperature is a constant. Stagnation temperature will be the static temperature plus V squared all over 2 Cp. So that would be, and this would be the case right here at point 1, and it would be the same thing at point 2 if the flow is indeed adiabatic. Okay, so we're going to check. There's a question mark here. We want to know if that stays the same through that flow, and if it does, then we can conclude that the flow is adiabatic. So we're given some information. We're told that T1 is 529 Kelvin. We're told V1 is 230.4 meters per second. We're told T2 is 475.7 Kelvin, and V2 we're told is 400 meters per second. And then the specific heat at constant pressure for air, you can look that up at a table, and it's about 1,004 joules per kilogram Kelvin. So we can plug these numbers in and then calculate what the values come out to be. So if you do this, if you plug these numbers in, then what you get from the left-hand side here, this one, you'll get that that value comes out to be 555.4 Kelvin. And then if you do it for the right-hand side here, that will come out to be 555.1 Kelvin. So they're close enough to say that yes, indeed, it's going to be adiabatic, because the stagnation temperature of about 555 degrees Kelvin, or 555 Kelvin, is the same at both. So we can say that the stagnation temperature is constant. So we'll say that the flow is indeed adiabatic. Okay, so again, part A we found just by checking to see if the stagnation temperature is a constant, because that would be what would happen if the flow was adiabatic. Now for part B, to find the forces, that will be an application of the linear momentum equation. Since we're trying to find forces show up in the linear momentum equation. Let's go ahead and apply the linear momentum equation to a control volume that cuts across the attachment flange, crosses the exit plane, and then looks like that. So that'll be our control volume. We'll put a coordinate system on there since we're dealing with the linear momentum equation. So we'll call that the x direction. We'll call that the y direction. And we need to apply the forces on here. So we'll just call that Fx, and we'll call this Fy. These are the forces that this part of the pipe applies on the control volume. So it's the forces this part of the pipe is applying. That's what we're trying to find. We're trying to find the Fx and the Fy. So let's go ahead and write out the linear momentum equation in the x direction, and then we'll also do it in the y direction. So in the x direction, we're going to get the following. So hopefully you remember the linear momentum equation from earlier in the course. So there's the linear momentum equation. We're using a coordinate system that's fixed, so we don't have to worry about the acceleration term in the linear momentum equation. Now let's go ahead and write out things we know. So this first term will be 0 because we're going to assume that it's a steady state flow situation. We're not told anything about how the flow is varying with time or anything like that, so we won't worry about that. We'll assume that it's steady state. The body force will be 0 because we're neglecting gravity, so nothing to worry about there. Let's do the momentum flow rate terms at the inlet and outlet. So at the inlet, let's go back up here. So we're talking about right here. The velocity there will be v1 in the positive x direction. So it's v1 headed that way, and that's in the positive x direction. And then the area there will be the pi d1 squared over 4. So there's the d1. Pi d1 squared over 4, but the normal vector points in the negative x direction. So when we do the dot product down here, we'll get a negative. So let me write this out. So we're going to have v1 in the positive x direction. And then here we'll have a minus rho v1 pi d1 squared over 4. So that's the momentum flow rate at the inlet. Now let's look at the outlet. So the outlet is down here. Well, immediately we see that the velocity here is in the y direction. So this is v2, and it's purely in the y direction. So that part we're not going to have to worry about because the ux velocity is 0 there. So this is the only momentum flow rate term we have to worry about. Okay, now let's do the surface forces in the x direction. So clearly we have the applied force that we're trying to find, Fx. It's right here. The other surface force we have is actually a pressure that's acting on the surface here, because we were told the pressure at the inlet is 871.7 kilopascals absolute. So there's some pressure acting on the surface. Let me just draw. It's getting a little busy here, but there'll be a pressure force that this fluid exerts on that part of the control volume. So that would just be P1 times d1 squared over 4. That's in the positive x direction because it's pointing to the right. And then what I'm going to do is I'm going to use a gauge pressure everywhere. So if I use a gauge pressure everywhere, then everything along the surface is 0, right? Because it's all exposed to the atmosphere. Down here, the pressure is different from, well, potentially different from atmospheric. We don't know what it is yet. But that pressure force would act in the vertical direction, so it doesn't even factor into it. So I'm just going to go ahead and use the gauge pressure for this, and that'll be our only surface force besides the Fx. So let's go ahead and write that down. I'll keep it in my blue ink here. So this will be plus P1 gauge times pi d1 squared over 4. So let me go ahead and rearrange that. So we'll have Fx is equal to minus rho v1 squared pi d1 squared over 4 minus P1 gauge times pi d1 squared over 4. All right, so that will be our force on that side. And we can plug in the numbers for that. If we do that, I ended up getting minus 19.6 kilonewtons when I plugged in the values. By the way, in order to plug in the values, we need to use the density. We weren't told the density of the air. Let me go back up here. We're not told the density of air here. We're given the pressure and the temperature and the velocity, but we're not given the density here. So since we're dealing with a compressible flow, we should calculate what the density is from the ideal gas law. We're given the pressure and temperature so we can find the density there. In fact, let me do that down here. I'll just make a little note here. Rho 1 will be P1 all over RT1, right? And the P1 was here we have to make sure we use an absolute pressure because we're using the ideal gas law. So the P1 absolute is 871 kilopascals, absolute pressure. R, this is a good number to remember because we deal with air all the time, 287 joules per kilogram Kelvin. And then T1, we need to make sure we're using an absolute temperature there as well. So that's 529 Kelvin. Those are all given. so that your rho 1, when you plug in all the numbers, is 5.738 kilograms per cubic meter. So that's the density I used up here. I should probably put a subscript 1 to make it clear. So in writing this out, we know rho 1, we just calculated it. We know V1, that's given, D1 is given. P1 gauge would just be this 871.7. Let me actually write that one down too. P1 gauge will be the 871.7 kilopascals minus 101 kilopascals, because it's going to be the absolute pressure minus atmospheric pressure. So that's what P1 gauge is. Okay, so that's the force in the x direction. We need to do the same thing in the y direction. So we'll apply the linear momentum equation in the y direction. So we'll write that out in its full glory. Okay, so here we are in the y direction. Let's do this easy things first. The first term is going to be 0 because, again, we're dealing with a steady state. The body force will be 0 because there is no gravity to worry about in this flow. We were told not to worry about that. The momentum flow rate out of the control volume. Well, let's go back up to the picture. You'll see here at location 1, there is no y component to the flow. The flow is purely in the x direction here. So we don't have to worry about it there. However, here we do have to worry about it. We'll have the y component of the velocity is going to be a minus v2 because it's in the minus y direction. And then the area will be pi times d2 squared over 4. And that's also that normal vector. Let me just show it. That normal vector is also in the minus y direction. So when we do the dot product between the area and the velocity, it'll give us a positive 1 because they're both pointing in the same direction. So let's write that down. So this will be minus v2. And then when we do the dot product, it'll be a positive. So that's what we get for the momentum flow rate. Now let's do the surface force. Well, here we have the applied force. That's the Fy that we had over here. This is the force in the vertical direction that this part of the pipe applies to the control volume. And then as far as pressure forces, this pressure force here won't be a factor because that's only in the x direction. We'll again assume gauge pressure all along the surface, so that's 0. Atmospheric pressure on the outside surface, that's just 0 gauge pressure. The only pressure we have to worry about is the pressure right here at the exit, P2, and that one would be pointed upward. So that would be P2 times pi d2 squared all over 4. Sorry, it's kind of messy there. But that's pointing in the positive y direction because it's acting inward on the surface. So let's write those terms down. So we already have the Fy, and then we'll write the pi 2 gauge pressure times pi d2 squared all over 4. And I'll come back to what this P2 gauge is in just a moment. But let me just go ahead and rearrange this equation as Fy is equal to minus rho v2 squared pi d2 squared over 4 minus P2 gauge times pi d2 squared over 4. Okay. And by the way, the density here would be rho 2. This is the density at the exit. Again, because we're dealing with a compressible flow. So we need to figure out a couple of items here. Number one, we're going to have to figure out what the density is at the exit. V2 we were given. D2 we're given. And then we also need to find P2 gauge. Okay, so let's first of all find the density at the outlet. Previously at the inlet, we used the ideal gas law because we knew the pressure and temperature there. But at the outlet, we only know the temperature. We're not told the pressure at the outlet. And I'll come back to that in a moment. So we can find the density at the outlet in a different way. And the way I'll do it is just through the mass flow rate. I know since this is a steady flow, the mass flow rate is going to be a constant. The mass flow rate coming into the control volume will be rho 1 V1 pi D1 squared over 4. And then going out will be rho 2 V2 pi D2 squared over 4. Right? This is just saying that the mass flow rate's a constant. Well, I know all of these terms on the left-hand side. And on the right-hand side, I know the velocity and the diameter, so I can then solve for the density. I'm not sure if you can hear the noise in the background there, but there's some construction going on where I'm located, so it's kind of loud in the background. I apologize for that. So let me just make sure I get everything done correctly with my algebra. So here is how we would find the density at the outlet. All I did was just take the mass flow rate, set it equal to a constant because it's steady state, and then just rearranged so I'm solving for the density at the outlet. And I think I got it all right there. There we go. So we can solve for that density at 2. And I don't think I actually worked out the numbers for that, but that's how you would do it. You can plug in the velocities and diameters and figure it out. Okay, so that gives us the rho 2. Now the last thing is the gauge pressure there. And this one is a little bit trickier. Now, I don't think I've mentioned it in lecture yet, but in pretty much everything leading up to this point in the course, we've said that when you have a free jet, the free jet's pressure is equal to the surrounding atmospheric pressure. And that's true if the flow is subsonic. Okay, so if the Mach number is less than 1 at the outlet, then it is definitely true that the pressure in the jet will equal the pressure of the surrounding atmosphere. However, when you start dealing with flows that are sonic or supersonic at the exit, it is possible that the exit pressure and the surrounding pressure can be different. And we'll cover that when we start talking about converging diverging nozzles. So to figure out what's happening here, we should just double check what the Mach number is at the exit. Okay, so what I want to do is find the Mach number at the exit. And the Mach number at the exit is going to be V2 all over C2, where C2 is the speed of sound there. So that'll be V2 all over square root of KRT, T2. And we know what V2 is. That was given as 400, I believe, 400 meters per second. K for air, that's the specific heat ratio, that's 1.4. R, of course, is 287 joules per kilogram Kelvin. And T2 we were given in the problem statement as 475.7 Kelvin. And like I said, V2 we were given, that was 400 meters per second. So we can plug these numbers in, and you'll find that the Mach number at 2 comes out to be 0.91. So this is a subsonic flow at 0.2. So even though we have a converging diverging nozzle, the flow coming out of it has a subsonic Mach number, and since it's subsonic, then we know for sure that P2 will equal the surrounding atmosphere. And since I'm working in terms of gauge pressure, P2 gauge would just be 0 because it's just atmospheric pressure. So since we have a subsonic Mach number at the exit pressure will equal the surrounding atmospheric pressure. So this term right up here will just disappear. We don't have to worry about it. And then we can go ahead and plug in the numbers for that. And what you'll get is Fy will come out to be minus 9.64 kilonewtons when you plug in the numbers. Now you might ask yourself, how would we have tackled this problem if the Mach number was greater than or equal to 1? Well, if it was equal to 1, so if the Mach number at 2 is equal to the 1, then P2 would be equal to the sonic pressure, P star. It would be the pressure when the Mach number is 1. And that, I'm not sure if we've covered that in lecture yet or not. But we would know that the pressure at 2 is equal to the sonic pressure, which we may or may not have covered in lecture yet. And if the Mach number here was greater than 1, then things get a little more complicated. We have to see whether or not the flow is over or under expanded. And again, topics we probably haven't covered in lecture yet. So you don't have to worry about those. Fortunately for us, the Mach number is less than 1 at the exit, so that means the exit pressure will equal the surrounding atmospheric pressure. So just keep that in mind, that whenever you have a free jet, if the Mach number is less than 1, it will be the same as the surrounding atmospheric pressure. If the Mach number is equal to 1 or greater than 1, then it gets more complicated, and that's something that we'll address in lecture at a different point. Okay, so anyway, hopefully this problem makes sense to you overall. Just kind of a quick recap. We checked, first of all, to see if the flow was adiabatic by seeing if the stagnation temperature was a constant. That's what we did here. We found indeed it was adiabatic. And then for the second part of the problem, to find the force, we applied the linear momentum equation on this control volume using that coordinate system. And the only real complications in that linear momentum analysis were, number one, we had to find the density at the inlet. There we used the ideal gas law because we're dealing with a compressible fluid, so we should use a compressible gas, so we should use the ideal gas law for that. And then the other complication was at the outlet, we also had to find the density there. There we just used the mass flow rate being constant. The other thing that was a complication was just determining the pressure at the outlet. And since the flow there was subsonic, we know the pressure is equal to the surrounding pressure. All right, we'll go ahead and end the example there.